So, what's on the rest of your minds? Yes.
I have 2 questions about the practice test.
Okay.
For number 6.
You can skip that one.
Skip that one.
Yeah, I don't really know why I left that on there because relative velocity is not on the test.
Okay. Okay. Number 7. The math kind of confused me. Could we go over that one together?
Absolutely. So, in terms of the physical setup and even the numbers given, I believe this one is very similar, if not the same as one we did in class, where we've got the 2 objects hung over the pulleys. One of them's hanging straight down, the other is sitting on the table, and therefore some form of friction is going to act on it. Now in class, we looked at this with the idea that the system will begin moving. But here, that's not immediately clear whether it's going to move or not. And so the first question is, will this system begin sliding? Why or why not? And so we need to think about what would cause this to start moving, and in what scenario would this system begin sliding if we just set it there and let it go on its own?
Wouldn't it be if the box 2's newtons are bigger than box 1's? Because it would pull it down more.
Which one are you considering box 1 and which one is box 2?
Box 2 is the one on the right. Box 1 is the one on the table.
Okay. Now, for this system to remain in place, what force would be holding it in place? Keeping in mind that the whole system has to move as one.
Frictions.
Friction. And which of the 2 objects has friction on it?
First one.
The first one. So, some force of friction would have to act to hold this block in place. And that friction would need to be overpowering whatever force is trying to pull this object to the right. Now, just looking at box 1 by itself, that means that friction would have to equal or overpower the tension. And that would be the same tension that is acting on this object. So, let's look at very quickly net force on object 1 in the x-axis. You've got force of friction backwards, tension forwards. And for this thing to remain in place, those 2 things are going to have to cancel out. Static friction is going to have to be equal to or greater than the tension in the rope. Question?
This is kind of just like an overall question. So when you're doing this, you're looking at like what affects the x plane and then what affects the y plane?
Yes, whenever you want to do net force, you need to look at each plane separately. Just because we can't technically add a y to an x directly. Does that answer the question? Okay. So yeah, this right now is x-axis forces on box number 1. There's only 2 of them, tension forward, friction backward, and they're going to have to cancel out for the box to remain in place. Now, from box 2's perspective, so I'm going to do net force y on box 2, because there's only y forces on box 2, the hanging one. From box 2's perspective, tension has to, if nothing is moving, so again, net force equals 0 if everything is being held in place. Tension's going to hold it up, and that tension is going to have to oppose the weight of box 2. So I'm wanting to show this to kind of show basically the transferring of force from one end to the other. from box 2's perspective, gravity's trying to pull it down, tension is trying to hold it up. And if the box isn't moving, these two things must be canceling out, and therefore the tension in the rope would be equal to the weight of the box if it's not moving. In class, we looked at a scenario where they are moving, so instead of adding up to 0, they add up to MA. But here, if it's not moving, they'd have to add up to 0, because if you're not moving, what's your acceleration?
0.
0. If your acceleration is 0, net force equals MA is 0. So from box 2's perspective, the only two forces on it are friction down, tension up. That means that the current tension, if nothing's moving, must be strong enough to counteract the weight of the box, the weight of box 2 specifically. And note that the numbers listed here, the 50 newtons and the 100 newtons, are the weights of the boxes, not their masses. You know this because it's in newtons and not kilograms. So, we can actually go ahead and quickly figure out what tension would need it to be. Tension minus 50, because gravity points down, equals 0. Therefore, tension is 50 newtons. And that's the same tension up here, meaning force of friction in order for friction to hold up this whole process, it's going to have to be greater than or equal, like the maximum value of static friction is going to have to be greater than or equal to 50 newtons. Since 50 newtons of tension is what's trying to pull box 1 forwards, and friction's trying to stop that. So just taking that 50 newtons of tension, plugging it in here, force of friction plus 50 equals 0. Move the 50 to the other side. Force of friction, you know what, I extrapolated a few things. Does that make more sense? Okay. That's fair. Let me see if I can explain it again. So, starting with box 1, again, we've already laid this out for it. Force of friction backwards plus tension forwards must add up to 0 if the box is to remain in place. We've already figured out what the tension would need to be to hold everything in place. If nothing was moving, tension would have to be 50 newtons. If we plug that tension in here, the equation would then look like static friction plus 50 equals 0. Does that feel okay so far? Yes.
Would the force of friction be negative since it's going in the left?
Yes, and that's where this negative ends up, or comes from. Because here we'd have to bring the 50 to the other side, so by subtracting it over, and then we would get the required force of static friction to be 50 newtons leftward. This would be the required minimum amount of static friction to hold everything in place. If static friction is less than this, it's going to start moving, because then it's not enough to hold it still. So that was the goal here, figuring out what the minimum requirement of static friction would need to be. If static friction is less than 50 newtons, the system's going to start moving. Question?
I'm not sure if you said this, but why wouldn't force of gravity be mass times acceleration? Or gravity?
It is.
So why is it 50?
Because this is the force of gravity. See, it's in newtons.
Okay.
So this is the weight of the box. We weren't given mass, we were given weight. And this is already, this is the answer of mass times G.
Okay.
Does that help?
Yeah.
Okay. Yeah, so note again the units that you're given in any sort of a problem, because that can make sure that you are clear on what is being told to you. Right now, at this point, This force of static friction needs to be at least 50 newtons to the left in order to hold the entire system in place. Now, the way that static friction works is that it can increase up to a certain maximum before it breaks, and the coefficient of static friction, which in this scenario is 0.55, represents the maximum that static friction is able to be before it breaks and before things start moving and before kinetic takes over. So if we use that static mu, the 0.55, we can see what the maximum static friction in the system is able to be. So, force friction static is greater than or equal to normal force times mu static from your formula sheet. Actually, no, it's less than or equal to, sorry. So now we're going to calculate what the force of static friction actually would be based on that mu, or at least what its maximum could be based on that mu. We were given the static mu. What value should we plug into normal force right here? $100. Very good. That's because this box has a weight of 100 newtons pulling down, and the only two Y forces acting on that box as it sits on the table are gravity down and normal force up. So for that object specifically, and I'll show that very quickly. So these are the Y forces on box number 1. There's only two, normal force up and gravity down. They must add up to 0 because box 1 is not accelerating up or down. It would only slide back and forth or no sliding at all. So no matter what's happening in the X, this is going to be box 1's Y axis. It weighs 100 newtons down, therefore the normal force on box 1 would be 100 newtons in this case. And we can plug that number into the friction formula. And that means the force of static friction on this box has a potential maximum of 55 newtons. Is that enough to hold everything in place? Yes, because we figured out friction has to be greater than or equal to 50 to hold everything in place, and its maximum here is 55. This is enough static friction to lock everything down, to keep box 1 from sliding. And if box 1 doesn't slide, box 2 is not going anywhere either because they're physically stuck to each other. So all of that to arrive back at the conclusion, no, nothing here is going to move. Static friction is strong enough. Now, do keep in mind, I have said I make the practice test longer and more difficult than the actual test. The goal for the practice test question was to kind of step through the realistic logic of what would need to happen here. On the test itself, I would tell you what you need to know to kind of skim through this. Like I would tell you it moves or it doesn't move, to save you time. Practice test meant to kind of show you the realistic logic of this. Actual test, something I want you to be able to do quickly and comfortably. I would tell you what you need to know just to get to the math that I'm actually testing you on. Anyway, question B says draw a free body diagram, so just draw all the arrows and solve for every force acting on both of these objects. We've kind of already done that actually in getting to the answer, will things slide? Because we already know the weights of both boxes. We figured out what the tension would be if things aren't moving. We figured out what normal force is, and we figured out that static friction has a maximum of 55. It would only need to use 50 of that 55. So in answering A, we've already answered B. How's this one feel? Excuse me. Does this one feel better?
Yeah.
Okay. So, what else is on your minds? Do not feel pressure to have any questions immediately. I'm kind of thinking of this as basically just a study session with you guys. We don't have to be talking 100% of the time. Nope, lost my train of thought already. Note that I am also happy to look at homework and stuff, because I do recommend doing that as study stuff. It's a good chance to ask if there's any homework questions you've been stuck on. But if you don't have any questions at this immediate moment, we can like pause the lecture here and just kind of have a study time, or you guys can head out early, whatever you're feeling, whatever you think will benefit you most today, because I assume you guys are taking the test today, if you haven't already. Again, the purpose of this is to do whatever will benefit you most. If that's studying quietly, great. If that's going home to take a nap, also great. So, there's nothing immediately on your minds. I'm content pausing here for a minute. And let me know whatever pops into your heads. Alternatively, I can just ramble about something, but whatever is most helpful. Just gonna pause the recording to prevent dead air. Humans have a tendency to remember things at funny or inconvenient times, and that is okay. 10 on the practice test. All right, we're gonna drop a baseball from the top of a building. Basketball, excuse me. Now, I had one student ask me, do you have to do this with energy calculations? And technically the answer is no. Like, you could do definitely A, possibly even C, with just old-fashioned Fantastic Four equation 3 and 4 type stuff. So if you read this and you think, my first instinct is use those old formulas, just do it. Unless I ask you for energy-based calculations, just go with whatever best works in your head. The only one of these three that requires energy is B, and that's because it specifically asks for EPE stuff. So I've got energy stuff here for A and C also, but technically you could do them without energy stuff.
So how do you know that those are the things that fill in? Like, you have the sum of energy is equal to sum of energy final.
Mhm.
How do you know that you put GPE for that one and
Well,
energy for that one?
We begin the question with the basketball falling from the top of a 10-meter tall building. As it falls, what's going to happen to it? So remove from the question real quick, but what's going to happen if you drop a ball off a building? It's going to descend and it's eventually going to hit the ground. We've been asked, what will the ball's top speed, I left the word out, top speed be the moment before impact. So this is the point, we're gonna pause time, the moment where height is 0, but before collision has actually started. So the ball is as fast as it's gonna get. At that lowest point, all of the GPE it had at the top will have drained, because now we're at height of 0 at that last possible second, and you're moving as fast as it's going to possibly go. So at that moment, all of the GPE it had has drained and turned into KE. Because it was initially up at the top of the building, it had a lot of height, a lot of energy stored in that ability to fall. As it falls, all that energy gets converted into KE. And it's basically true of any falling object.
So why would you put GPE 0?
GPE final is 0?
Initial. Oh, initial, sorry.
Yeah, sorry, that's GPE I, GPE initial. So on the total energy initial side, initially GPE is the only type it has before it starts moving. And then I admit, when I was doing these in class, I tended to show, everything on all sides, even if they happened to be 0. So if I wanted to do this in full, and also try to make it a little more legible. So looking at all forms of energy present on both sides, its initial GPE is based on its initial height, which is not 0, that's the 10 meters. Its initial KE is 0, because it wasn't falling yet, it's just being held in somebody's hands. Afterwards, all of its GPE is gone, because it's now at a height of 0, at that last possible split second before impact. So there's a moment where height is 0 before it actually begins the collision process. But it will have some amount of KE because now it does have a velocity. In fact, the highest speed it can possibly have right before impact. Does that help?
Mm-hmm.
Okay. And again, you don't have to think about it as energy. I just did it this way to demonstrate that it could on my answer key. And the idea again being, initial GPE is going to turn entirely into KE, and that's going to determine the speed that the ball is moving at. Weirdly, there's now mass on both sides, so the mass of the ball is actually kind of irrelevant for this part of the process. Kind of like how you don't really need to know the mass of the ball to use the first 4 formulas we talked about. There's no M's in any of those. But I'll include it here for completeness sake. 0.2 kilograms times the magnitude of 9.8, because this formula has an absolute value bracket in it. Height of 10 meters. Just going to cut the zeros out, equals 1/2, again, times mass of the ball, times that final velocity squared. The masses cancel, send the 1/2 over, take the square root of both sides. That would look, my markers are all dying. Where's my trash can? Now I can't even try to do it. Upsetting. I was gonna miss anyway, but now I don't even get to attempt. Masses cancel, so we're gonna do 9.8 times 10 divided by 1/2. Take the square root of that. And assuming I was right before, that should give 14 meters per second down. Yes?
Would it be okay if we wrote that second line of formula on our formula sheet, the GPE I plus KE equals final?
Yes. This would be an okay formula to have. I would actually, for completeness sake, if you wanted the most general form possible, I would add initial and final EPEs as well, because that's another form of energy that could exist. And then I would just recommend in each question thinking, is there an elastic object that has EPE in either the before or after stage? So, again, most general possible thing, all forms of energy initial, whatever types, some of them might even be zero, but all of the initial forms must add up to the sum of all of the final forms. Certain things might be zero on one or both sides, but the totals must match. So yes, you can write that on your sheet. That's a good idea. And this, doing part A of this one specifically, the EPE is just zero on both sides because there's no EPE present, just if it's being held or just if it's falling. There's EPE present in part B, but not in part A. So in part A, both of these just kind of fall out. So if you do write down this form, just use your discretion. Some forms of energy are going to be zero, depending on the question. I think I rambled for a sec there. Questions on this first part? All right. Now, part B. This is the one that absolutely needs to use energy considerations, since it specifically involves EPE and spring constant. There is another formula with spring constant in it, but I told most of my classes, I hope I mentioned it out loud here, you guys aren't actually going to need, it's labeled as Hooke's law. You're not going to need that spring force formula. The test just didn't end up including it, and I don't want to confuse anyone. So this formula, Hooke's law, F spring equals negative K times delta X, that's not on the test. So here when I ask you for spring constant, there's only one formula that has it that is on the test, and that's the EPE formula. So that's meant to be the hint. EPE is involved in this one. So in part B, the ball is actually going to now hit the ground. It was now moving at 14 meters per second right before impact. Upon impact, that velocity is going to drop to zero for a second as the ball squashes. Because in the moment where it's squished, velocity drops to zero. It's not moving in that split second. And we know it's not moving because it's going to go from negative 14 to positive 14 once it rebounds. And there needs to be a point in the middle there where it stops to zero if it's going to turn around. So the moment in time we're examining now is, initially, it's moving at top speed before impact. Then, upon impact, it's going to squish some distance, and all of its KE is going to form into EPE instead for a split second, so that that energy is stored and not wasted. Because if a non-elastic object hits the ground, it just kind of all goes away and it doesn't rebound. It's because it's not stored for a second, it just gets wasted. That's why only elastic objects bounce. Drop an anvil off of a building, it doesn't rebound, it just makes a crater. So, for part B, same starting point, examining the energy present on both sides. On the initial side, we're still at height 0. That hasn't changed. So there's no initial GPE. There is KE, because the ball is moving at that top speed. And it hasn't squashed yet, it's not compressed yet, so there's not any EPE yet in our new before state. Sometimes I find it helps to draw out before and after states, if it helps illustrate the point. So our new before state is the paused moment in time, right before impact, where we're moving at top speed. In that position, top speed means we have kinetic energy, but we haven't squished yet, so no EPE, and we're at height of 0, so no GPE. On the after side, we're still at height 0, so no GPE. We've stopped moving, so there's no KE. And we have now squished a little bit, so there is going to be EPE. How's that feel? Okay. Now, our goal here is to solve for spring constant because we are told the change in size of the ball upon impact. Again, it's hard to see, it's pretty much near impossible to see with your human eyeballs, but the moment of impact, the ball does pancake slightly, and we've been told that the change in size by how much it pancakes. And that's technically true of anything that bounces. So basketballs, the bumper on a bumper car, in impact it always deforms for a minute and then springs back to normal. I mentioned I watched a lot of Mythbusters as a kid. One episode, the two hosts decided to, at least for a minute, test the elasticity of a human face. And so one host slapped the other on freeze frame camera, on slow-mo camera, and human faces do this too. It was an interesting video of one host's face just having a ripple across it that you don't see normally. Anyway, we've got everything we need to find, well actually we kind of already found the initial KE, so we're just going to solve for it again. So that same speed we found a second ago determines how much KE the ball had. In terms of EPE, we're solving for K, and the ball shrinks from 24 centimeters to 18 centimeters. Again, this delta X here is meant to represent the change in size. So here it gets 16 centimeters smaller, and so that is why I plugged in 6 centimeters converted to meters. 6, not 16, 6. Even if you plug in a negative number there because the ball shrinks, the squared gets rid of the negative. So that's why I always call it change in size. Whether it's growing or shrinking, EPE doesn't care. Because whatever positive or negative you put here, the square is going to get rid of any potential negatives. So that's why this formula works for, you know, pulling a spring out, but also compressing a basketball in. And working this through, we should arrive at a spring constant of approximately just shy of 11,000 newtons per meter. So it takes a lot of force to stretch out this basketball by a whole meter, which makes sense because if you had a normal regulation basketball, I don't know if it physically could be warped to 1 meter longer before it breaks. And you obviously can't make it 1 meter shorter because then it would just vanish. Yes?
Why is GPE for both 0?
That is because for both the before and after of this specific scenario, the ball's already on the ground. So height is 0 for both sides of this. And if you plugged in the actual formula here, the height you plug in both sides would still be 0 because the ball is on the ground for both parts of this. Does that answer the question?
Mm-hmm.
Then the last part, assuming total energy conservation and no friction, to what height will the ball bounce to? So at this point, whatever energy it has is going to eventually turn back into GPE as it rises again. What I did here is I turned the EPE that we just found back into GPE, but you could also do KE turning back into GPE, because it doesn't really matter what your initial state here is. What matters is that you set the final state to that maximum height again. As long as all of the energy eventually turns back into GPE and figuring out the height at which it will rest once all the energy is back into that form. And if no energy was lost at any point in time, and you do all your math right, you'll find it actually rises back to the height it started at. Because all the energy is just going to turn back into its original state at its starting height. Now, realistically, does that ever actually happen? No, and that's because realistically, you're going to lose energy every single time the ball strikes the floor. Because a weird quirk of impact is even with the most elastic basketball in the world, you're still going to lose a little bit of energy on impact with the floor. And that's ignoring air friction too. So you could buy the best turbo bouncy ball a vending machine can provide. It's never going to rise to exactly the same height. Assuming if you drop it, it's never going to rise back up to exactly the same height. It's going to keep decreasing every single time, realistically. Now, if you threw it at the ground, it would rush back up past the original height, but that's a different case. If you throw it at the ground, you are giving it initial KE alongside its initial GPE. And so that's a different scenario. But if you're dropping it, realistically, nothing ever rises back to the same height. And it's also why there's some very good physics professors online who record videos of themselves hanging bowling balls from the ceiling, holding it right up to their face, and then letting it swing across and back to their face. They know full well, because you lose energy over time, the ball is never actually going to strike them, so they just stand right in its path. I don't have that set up, and I'm also a coward, so I don't do this, but the footage exists. And that's actually kind of what Chapter 6 is going to involve. We're actually going to study collisions, which is what's happening here, and look at what happens to the energy in them. Look at how it's lost, look at how much of it is conserved, look at the two different major types of collisions. So this is kind of a preview of next week, at least part of next week.
Do we have lab next week?
No, and that is because fall break has eliminated Monday and Tuesday from the schedule. So no lab at all next week. Enjoy your prolonged mini vacation.
Are you gonna post the test results
Well,
on Brightspace?
I keep forgetting to try to put grades on Brightspace. At minimum, you will get your test back. So next week, class will only meet Wednesday and Friday, because again, Monday's not gonna happen. On one of those 2 days, just depends on when I finish, we will spend a whole day giving everyone's tests back, looking over my answer key. And once you have your test, it's yours. Like you keep it, and my main goal with that is you can use it to study for the final, since the final is basically the 2 tests mashed together. So your test is a good study aid, and I let my students keep it for that reason. So next week, at minimum, you will get your own test back and know your score on it, at least from the paper copy in your hands. I'll be working on Brightspace. I'll be working on putting grades on Brightspace too. How you guys feel?
We'll see.
All right. Any other questions right now? All right. We can call this lecture here for right now. Do let me know if you have any other questions, either now or up until the test this afternoon. And have a great day. The test is going to go great. To those curious, I'm not done grading them yet, but the ones I have graded are looking good, so.
It's encouraging.
Yes, I'm saying it to be encouraging.